Thanks for joining our webinar. My name is Damien, and I'm here with Rajiv to share best practices for provisioning Amazon MSK clusters, and we'll show you how to use popular Kafka-compatible tools with your MSK clusters. For those new to MSK, MSK is a fully managed AWS service for Apache Kafka. Here's the agenda for the day. Today we will walk through how to right-size your Kafka clusters within or outside of MSK. Our goal is to provide you with tools and knowledge that you can use to right-size your Kafka cluster no matter where it runs, regardless of if it runs in EC2 or on-premise or in MSK. We'll also share some best practices for the life cycle of your MSK cluster and provide insight into our roadmap. Rajiv will then walk through how to use MSK with Burrow, which you might use to monitor consumer lag, Schema Registry for schema evolution control, and then finally deploying the REST proxy with MSK for public connectivity and to provide your clients with a RESTful interface. We'll start by walking through how to right-size your Kafka clusters. This might look familiar, at least the process might. Most customers, when they're right-sizing their cluster for the first time, they go through this process of guess and check. And if you're new to using Kafka, you're also probably going to hop online, spend some time getting to understand how Kafka supports I/O, what the bottlenecks are, and you'll probably look for best practices for provisioning. Using the results you find online, you'll realize there isn't anything out there that provides you with a starting point for provisioning your cluster. You'll then provision a cluster and enter this cycle of guessing and checking, using Kafka performance tests to see if the cluster can withstand your workload. If it can't, you'll scale the cluster up and try again. If it can, either you found the result you were looking for, or you scale it down, it being the cluster, and you might want to right-size it again. We've seen our customers do this a couple of times, and we've also seen that customers who are looking at MSK for the first time, we found that they are severely over-provisioning their Kafka clusters. Not all of them, but some of them are. And those clusters may be running on-premises or in EC2. We also find that many customers don't resize their cluster until there's a need to do it. So they start off with a cluster that works rather than starting off on the right foot from the beginning, and they end up spending a lot of additional money on that cluster over time for the capacity that they never ended up actually using. We also find customers find translating their cluster costs to MSK or other managed Kafka providers as something that is cumbersome, primarily because the cost models don't line up like for like. If you're looking at comparing the cost of using your Kafka cluster in EC2 compared to MSK or other managed Kafka providers, each of those models have a different cost structure. So what we did is we built a solution that helps you not only right-size your cluster, but also helps you compare costs. So this is where you can find it. What it is the calculator. It's Excel-based, and it's our first iteration at this right-sizing TCO calculator. You can download it by following this link, or you can visit the Amazon MSK Best Practices section in the user documentation. You can find it there. The calculator is simple and easy to use, and it only requires a few of your inputs. You provide what your expected ingest rate is, replication factor, how much egress is leaving the cluster, your retention time, and the average EBS utilization that you would expect to use over any given period of time. There are also a couple of advanced settings like encryption, which will impact performance if you enable it, and will also result in the need for additional cluster capacity. You can also specify the amount of engineering time that you'll save by moving to a managed service for Kafka, and specify whether or not you're currently using EC2 reserved instances. There's some other advanced settings here, but you can go ahead and change those if you feel like they're needed. And from that input, there's a very straightforward output. We tell you how many brokers of a given broker type would be required to support your workload. And we'll also break down the costs for that workload. We'll break that down into broker, storage, and data transfer, and also summarize this with a total monthly cost, and then break that down into a effective $ per gigabyte cost. It's important to note that the data transfer cost here is the cost from your clients that we're estimating. The clients will pay data transfer for traffic to and from the cluster, but they won't pay for data transfer as a result of replication with MSK. So we're incorporating that here to give you a full picture of what your costs are when you are using MSK. We'll also break down a comparison of this, the MSK costs compared to what you might pay self-managed in EC2, and then also if you are including the costs of engineers that are effectively saved by using a managed provider, we break that down as well. Now, there are a number of underlying assumptions that went into this calculator. First, it's important to note that this isn't an end-all, say-all calculator for Kafka. There are a number of variables that you can tune on your own that will impact performance and your capacity consumption within the cluster. This calculator doesn't give you all of those knobs, but it gives you a great starting point for provisioning a cluster for a typical production workload and provides a basis for comparing costs against alternatives. What you're seeing here is the results of a round of performance tests that we ran against an MSK cluster, and we use this as a basis for this right-sizing calculator. We tested a number of scenarios varying throughput and consumption, and we also made a few underlying assumptions on what we are targeting. One is our goal was to maximize throughput, but also do it in a way that minimized put latency or write latency. And minimizing means that we are maintaining a P99 of 100 milliseconds or less on write latency. There's also a number of variables we didn't test, like changing the broker type to, say, an M5 2x large, or using producer ax equals all. Nonetheless, we believe the results can be used to inform a general recommendation on how to provision a Kafka cluster. Let's look at row one. In our testing, we started out by hammering the M5 extra large cluster with 15 brokers, and we hammered it with 500 megabytes a second of traffic. You can see that Kafka was struggling to ingest this traffic and could only accept 414 megabytes a second, or effectively that is 28 megabytes a second per broker in the cluster because there's 15. The write latencies were also quite high. P99 was above 200 milliseconds, which for a real-time workload and based on our customer feedback, that generally isn't acceptable. We then reduced throughput from the producer side to a point where P99 write latencies fell below 100 milliseconds and found that happened around the 8 megabyte per second mark for the M5 extra large set of brokers. We then applied, using this result, we then applied the instance type normalization factor to back into the throughput that each broker could support across the different instance types. So note that if you have looser latency requirements, so if your P99 write latencies can be higher than 100 milliseconds, you could probably get up to 4x more throughput than the calculator assumes. Also note, throughput-wise, we're being conservative, primarily because we're balancing throughput and latency to the same time. These tests show that Kafka can actually support a lot more throughput than what we are recommending you start with from a provisioning perspective. However, being conservative gives you additional capacity to handle operational events if they are to occur, and gives you the capability to adjust for changes in traffic patterns without having to scale up the cluster. You can also see that this produces a $1 per gigabyte estimate for this given performance test, which we found that most customers, given this cluster in these different scenarios, will effectively end up paying anywhere between 3 and 5 cents per gigabyte ingested. So here are a few takeaways. As I mentioned, this calculator is to get you started. It should get you in the ballpark for most production workloads. There are definitely edge cases out there that it does not account for, but we do recommend that you test your production requirements against the cluster after you've provisioned it. The costs are normalized here. The output within the calculator gives you a normalized cost per gigabyte, and this makes pricing comparisons easy. So if you are looking at the cost of EC2 or MSK or another Kafka provider, or managed Kafka provider, you can use this to compare the costs across those providers. Your latency requirements will impact how much you should provision. If you don't have a strict latency requirement as we have assumed you have in the calculator, then you can probably get away with provisioning less. And then finally, if you have any questions or feedback, feel free to post those in the AWS forum, and you can find a link to the calculator on the Amazon MSK user documentation page. So we're going to share a few additional best practices, and then I'll get into sharing what our roadmap looks like, at least a few of the roadmap items over the coming months. So after you've provisioned your cluster, we recommend that you set a CloudWatch alarm on the Kafka data logs disk used metric in CloudWatch to prevent running out of disk space. A good starting point is to trigger an alarm when this metric hits 85% utilization. When this alarm is triggered, you should increase broker storage either within the AWS Management Console or using the AWS CLI. Finally, make sure you're using the ideal retention settings on topics to minimize the amount of disk you use. You can also instrument this entire process automatically using an SNS notification that's triggered by the CloudWatch alarm, which triggers a Lambda function and then increases the storage. Let's talk about partitioning. From a producer's perspective, partitions maintain order for data. For example, you can have all events from a specific user ID delivered to a Kafka topic, and these events are stored in partitions in order. This might be accomplished by setting the user ID as a partition key on the producer side, where all events from a specific user are gathered and stored in order within a specific partition. From a consumer side, from a consumer's perspective, you can think of partitions as hoses that these applications drink from, or the consumers drink from. If you hold ingestion constant, the fewer partitions you have within a topic increases the amount of data flowing through a partition, which applies more pressure on consumers to process data at higher rates. Your consumers will have a varying degree of consumption capability depending on the application. So, as a rule of thumb, to get started, we recommend that you provision, when you're provisioning partitions, that you select you take the max ingest rate per topic in megabytes per second and you divide by 2. This will give you a good starting point for the number of partitions that you should provision on a per topic basis. We also recommend that after you create these partitions, that you leverage a partition key strategy that balances load across these partitions. That way that you are effectively load balancing, and not one single partition is hot, meaning that it's ingesting most of the workload from the producers, and that also increases parallelism across consumers. Because you're increasing parallelism and you're not ideally hitting any consumer bottlenecks for consumption, this generally means more partitions generally means higher throughput. Alternatively, if you know how much throughput each consumer can support per partition, then just simply use that in the denominator. And keep in mind that you need to ensure you have enough capability to catch up. So if your consumers fall behind, that they have enough capability on the application itself to ingest at a faster rate than the rate of data that's flowing through a partition. So here's a glimpse at our 0 to 6 month roadmap. This is not inclusive of everything, but this gives you a general sense of a few things that are coming. First is scaling out clusters. Shortly, you'll have the capability to add brokers to a cluster using the AWS CLI or management console. That'll give customers the capability to add additional headroom as their workloads, or add additional capacity to clusters as their workloads grow. We'll also be announcing an integration with Prometheus and support for JMX metrics, so that pre-existing metrics pipelines can quickly and easily take advantage of MSK without having to rewrite those pipelines. We'll also be supporting 2 AZ broker deployments. Today, you can only set up a cluster with brokers across 3 availability zones. Soon, you'll have the capability to set up the cluster across 2 availability zones. This is important for customers who want a lever to reduce costs, but also provide a high availability experience. We'll also be rolling out MSK in additional AWS regions, including those listed here. Delivering broker logs to CloudWatch logs. This will be a useful feature for customers who need to troubleshoot their application, or who are accustomed to troubleshooting their application using logs from Kafka. Shortly, we'll be providing those natively within CloudWatch. If you need access to those logs now, you can simply submit a support ticket, and our team will provide you with those logs. And then finally, we'll be announcing support for version upgrades that will kick off a rolling upgrade process across your cluster if you want to go from one version of Kafka to another. All right, I'm going to let Rajiv Chakrabarty talk about how you can use Burrow, Schema Registry, and the REST proxy with Amazon MSK.
Hi, thank you, Damon. My name is Rajiv Chakrabarty. I'm a specialist solution architect with AWS. And as Damon mentioned, I'm going to talk about utilizing some of these Kafka ecosystem tools with MSK. So currently, MSK provides, as a managed service, the topic storage part of Kafka, meaning that other tools in the Kafka ecosystem, like Kafka Connect, Mirror Maker, Kafka Streams or KSQL, Schema Registry, and the REST proxy, is not currently available as a managed service. However, as depicted on this slide, those tools are compatible with MSK and can be used with MSK when installed on EC2 instances or containers and self-managed by customers. So today, I'll be talking specifically about Schema Registry, the REST proxy, and Burrow. Before we dive into those tools, it is important to understand how the service works from a network connectivity standpoint. When customers create an MSK cluster, the Kafka broker nodes on EC2 instances and the Zookeeper ensemble is created and run in a service managed VPC, which is depicted as VPC1 in this diagram. They do not show up in the customer VPC, which is depicted as VPC2 in the diagram. However, ENIs, which are elastic network interfaces, are dropped in the customer VPC, which represent the broker nodes and the Zookeeper nodes. These ENIs get private IPv4 addresses from the IPv4 CIDR block of the VPC, actually more accurately from the subnet specified, and a private internal DNS. In addition, the bootstrap brokers get private DNS endpoints which are mapped to these internal IP addresses. These ENIs enable network communication between the customer VPCs and the service managed VPC. As shown in the diagram, producers and consumers then use these ENIs to produce and consume messages from the MSK cluster. You can also use other tools like the Kafka topics or the Kafka console producer or consumer and get cluster and topic metadata as well. Similarly, tools like Schema Registry, the REST proxy, or Burrow installed on EC2 instances in the VPC or with access to the VPC, either via VPN or Direct Connect or VPC peering, can connect to the MSK cluster and utilize the MSK cluster. All right, so let's talk about Burrow. So what is Burrow? According to the GitHub page, Burrow is a monitoring companion for Apache Kafka that provides consumer lag checking as a service without the need for specifying thresholds. So what is consumer lag? Consumer lag is a difference in offset between the producer head offset, which is the offset of the most recent message received by the broker of the primary partition, and the committed consumer offset. It essentially denotes how far behind a consumer or consumer group is in reading messages from a topic or topics. It denotes the health of a consumer or consumer group, as if it falls too far behind, more than the retention period of the topic, there could be data loss. It also indicates whether a consumer has stalled or failed. Now, there is a max lag metric available in the consumer. However, since it is reported by the consumer itself, if the consumer has stalled or failed, it would not be reported. Further, if wildcard topics are used, measuring lag can be difficult as lag is calculated per partition. If you decide to pick a few topics to check, then the problem could be on a topic that you're not checking. Further, the mechanism for alerting to a potential problem can be based on a simple threshold, as that does not accurately represent conditions like a sudden spike in message throughput with the consumer catching up. That would result in a false alarm. Burrow checks all partitions across all topics and measures lag over a sliding window instead of using thresholds. Burrow has a modular structure and uses a number of subsystems. Essentially, it gathers topic, partition, consumer, and offset information and stores it and makes it available via HTTP endpoints or by providing email or HTTP alerts. There is a Burrow GitHub wiki which explains each of these subsystems in detail and what their configuration parameters are. So how do you install and run this in the customer VPC and set it up to integrate with MSK? So the idea is to use an EC2 instance. You could also use a container, but the idea is that they have to run in the VPC and have connectivity to those ENIs that I talked about earlier. In addition, when you are creating an MSK cluster, you have to specify a security group. And if you don't, the cluster will essentially pick the default VPC, default security group of the VPC. That security group needs to enable communication on TCP over ports that would connect to either the brokers or the zookeepers. Typically, they are 1992 for plain text or 1994 for SSL or TLS for the Kafka broker nodes and 2181 for zookeeper. So you can open this up to a specific set of IP addresses, or you can open it up to another security group. Typically, when you install producers, consumers, or other tool sets on EC2 instances, you have to specify a security group for that instance, and you have to allow that security group or any EC2 instances or members of that security group to be able to connect to that security group that is associated with MSK. So in this case, for Burrow, I use an Amazon Linux too, so you can have other types of OSs that you can use as well. But Amazon and Linux 2 did not come with Git included, so I installed Git. Once you spin up these two instances and SSH into the instance, you can go and first get a version of Go that you'd like to install, because Burrow depends on Go. So once you download it and extract it into a Go tree, as explained, it is very important to follow the steps as explained to have a functioning Go environment. And then at that point, you can clone Burrow from GitHub and install it with Go. Burrow uses a configuration file, which is in the config directory, and is called burrow.toml. TOML, which stands for Tom's Obvious Minimal Language, is a configuration file format that is intended to be easy to read and write due to obvious semantics which aim to be minimal and is designed to map unambiguously to a dictionary. TOML's syntax primarily consists of key value pairs and is similar to an ini file. Burrow uses the Viper configuration framework for Golang applications. It also supports the config file in JSON and YAML. The configurations and its meaning are well documented on the Burrow GitHub wiki post, but for the purpose of connecting to MSK, the Zookeeper connect string, the Bootstrap broker settings are the primary ones that need to be updated. Those can be retrieved from the MSK console or using the AWS CLI by using list cluster or describe cluster, or for the Zookeeper connect string, for the Zookeeper connect string, or using the get Bootstrap brokers to get the Bootstrap broker information. So once you have Burrow installed, start it and test it out using curl. Okay, next let's talk about Schema Registry. So Confluent docs state that the Confluent Schema Registry provides a serving layer for your metadata and provides a RESTful interface for storing and retrieving Apache Ivor schemas. So what is a schema and why is it needed? When sending messages to Kafka, producers need to serialize the message into bytes, and in turn, the consumers need to deserialize the messages when reading. JSON is a popular serialization format, as it is language agnostic and relatively compact. However, it has a number of drawbacks. Primarily, since it has a flexible structure, fields can be arbitrarily added or removed, and data can even be corrupted. When that happens, downstream consumers are unable to interpret the messages correctly. What is missing is a contract between the producers and consumers. This contract is provided by a schema, which defines the structure of the expected messages, their types, and the meaning of the data. Further, with a schema, the messages themselves can be more compact as they don't have to include the structure in the messages. The Schema Registry is a distributed storage layer for Avro schemas, which uses Kafka as its underlying storage and supports the Avro format. An Avro schema defines the data structure in a JSON format. Avro requires schema not only during serialization, but also in deserialization. For the Schema Registry, this functionality is provided by the Avro serializers and deserializers. The Schema Registry stores schemas, versions them by subject, and provides schema evolution through compatibility settings. It uses a special compacted Kafka topic, by default called schemas, to store the schemas. The producers and consumers interact with Kafka as normal, sending and consuming messages, as seen in the diagram. However, the serializers register new schemas or schema versions with the Schema Registry and includes the ID of the schema in the message, which is then used to get the schema on the consumer side by the deserializer to deserialize the messages. So the Schema Registry lives outside the Kafka brokers, and as long as the Schema Registry URL can be accessed by the producers and consumers, this setup works. In the MSK context, MSK is the Kafka layer depicted in the middle of the diagram and can be connected to by the Schema Registry to store schemas. So the steps for installing Schema Registry are very similar to Burrow, as we'd already discussed. So essentially, you spin up an EC2 instance within the same VPC and make sure that the security group allows connectivity. Next, you go ahead and SSH into the EC2 instance and get the version of the Confluent platform that you want to install. So once you download Confluent, you can unpack it using tar. And then at that point, you have to go into the configuration file called schema registry.properties. The important settings for them are bootstrap servers and the listeners. Also, it is important not to specify the Kafka store.connection URL. The schema registry can use either Zookeeper or Kafka for primary election in case of schema registry clusters, and specifying the Kafka store connection URL directs it to use Zookeeper instead of Kafka. If you need to connect to a secure MSK cluster, then the Kafka store.ssl parameters need to be set. And to connect to the schema registry using HTTPS, you need to configure an HTTPS listener, and the SSL parameters need to be set. Once done, you can then start the schema registry and test it out with the Kafka Avro console producer and consumer. Right. Next, let's talk about the REST proxy. So the Confluent REST proxy provides a RESTful interface to a Kafka cluster, making it easy to produce and consume messages, view the state of the cluster, and perform administrative actions without using the native Kafka protocol or clients. So when is that useful? In general, when you're sending messages to Kafka from an app in a language that does not have a Kafka client support, or processing messages in a stream processor that doesn't support Kafka, but in the context of MSK, since MSK is designed to be available inside the VPC, the REST proxy provides a way to make it available to applications over the internet outside of the VPC without a VPN or a direct connect connection. It is important to remember that the official Kafka clients would not work against the REST proxy, and the apps would have to be written to make use of the REST proxy. In order to build a scalable and highly available architecture, you can run a cluster across AZs and put the cluster behind a load balancer. The REST proxy can support metadata requests, accept produce requests and send them to a Kafka cluster using a pool of producers, and it also uses a simple consumer by default to consume messages. It also integrates with Schema Registry and requires a specification of a Schema Registry URL for use by the Avro serializers. So how do you install them? Just like the other tools, the REST proxy can be run in containers or EC2 instances in the same VPC as the MSK cluster, or with access to the VPC and the MSK security group as explained earlier. Since you need to SSH into the instance, make sure it is in a public subnet with the security group attached to it having SSH port 22 open. Then download the Confluent platform. Once you unpack the tar file, update the Kafka rest.properties file, which is the configuration file for REST proxy. In it, include the MSK connection parameters, including the bootstrap servers, the Zookeeper connect string, and the schema registry.url. Then configure the listeners. By default, it will listen on all IPv4 addresses on the local machine. Also, update ID, which is used in generating unique IDs for consumers that do not specify their ID. The ID is empty by default, which makes a single server setup easier to get up and running, but is not safe for multi-server deployments when automatic consumer IDs are used. If you need to connect to a secure MSK cluster, the client.ssl parameters need to be set. And to connect to the REST proxy using HTTPS, the SSL parameters need to be set. There are many other configuration options, but these are the most important ones, especially for connecting to MSK. After that, start the REST proxy and produce and consume some messages from it. All right, that brings us to the end of the presentation. Now we have time for some questions.